Hi, good morning, and welcome to another webinar in the Industrial Heating Equipment Association's series on sustainability and decarbonization. I'm Jason Safars and serve as treasurer for the IHEA Board of Directors. And on behalf of the association, thank you for joining us. We are excited to continue this series on sustainability topics for everyone in the industry. I'd also like to announce the IHEA is launching the 2024 Industrial Heating Decarbonization Summit, held on October 28th through the 30th in Indianapolis, Indiana. The purpose of the summit is to forge a sustainable path to decarbonization for all companies in our industry. Registration for the summit is now open, so be sure to visit IHEA's website at www.ihea.org and check out all the details. Before we get started, I'd like to remind everyone that all attendees are on mute. If you have any questions along the way, please type them in the questions panel. The speaker will address the questions at the end of the webinar. Also, all attendees will receive a brief survey after the webinar. It'll take just a few moments to reply, and we appreciate your feedback as IHEA continues this critical initiative for the industrial heat processing industry. One last announcement, the webinar is being recorded and will be available in the sustainability area of the IHEA website within the next few days. As an attendee, you will receive an email once the link is available. Now I'd like to introduce you to the presenter for today's webinar titled Renewable Fuels. John Stanley graduated from Bradley University in 1985 with a Bachelor of Science in Mechanical Engineering. During John's time at Bradley, he worked for Kewanee Boiler Company as an engineering co-op student, gaining knowledge and experience with boilers, burners, and combustion controls. After graduating from Bradley, John continued his work in the boiler industry as a project engineer for Johnston Boiler in Ferrysburg, Michigan, where John managed various customer projects, including applications for non-typical boiler fuels. John then moved to Eclipse Inc., where he spent 20 years in various roles, including product engineer, product manager, manager of engineered systems, global industry manager for building materials, and finally, global industry manager for biofuels. In his last role, John spent several years focusing on the application of industrial burners for various types of gaseous and liquid biofuels. For the last 15 years, John has been working for Carl Doings Inc., initially as a regional sales manager, and now as Vice President of Sales and Marketing, responsible for sales in the Americas, as well as key account management for large OEM accounts. Carl Doings Inc. is a manufacturer of combustion controls products for all types of combustible gaseous fuels, and John also serves, along with me, on the IHEA National Board of Directors. So thank you, John, and we'll take it away.
Thank you, Jason. And good morning, everyone, to this morning's Industrial Heating Equipment Association webinar on renewable fuels. So renewable fuels are a sustainable alternative to conventional fuels, and in many cases can be used with conventional equipment without major change and/or expense. Since renewable fuels are produced from renewable sources, they can often provide for a reduction in carbon emissions in industrial processes, promoting a more sustainable environment. In this IHEA webinar today on renewable fuels, I will review the various types of renewable fuels available for industrial processes, the environmental benefits gained from using these fuels, and some of the challenges one might incur while applying the fuels to their process. The goal today is to provide you with some insight into how renewable fuels might play an important role in your carbon reduction plans for the future. Before we get started, we must first understand what we mean by renewable fuels. So in this basic sense, renewable fuels are fuels produced from renewable sources, which can be landfills or biodigesters, plants, or other natural feedstocks, or fuels produced from renewable energy sources. So why are renewable fuels important to us today? Renewable fuels are derived from sources that are naturally replenished and reduce our dependence on fossil fuels. which significantly reduces greenhouse gas emissions and can help to minimize the future climate change. So in today's presentation, we're going to talk about the various types of renewable fuels, look into some of the typical applications where these fuels can be used, what some of the environmental benefits are of using these fuels, and then a little bit on what some of the challenges are using the different types of renewable fuel. When we talk about renewable fuel types, we always start out with our discussion on biofuels. Biofuels could be landfill gas, digester gas, renewable natural gas, which we'll explain in more detail later, ethanol, biodiesel, or advanced biofuels, which is kind of a general term for a bunch of different applications for secondary processed biofuels. And we'll talk a little bit about synthetic fuels and their application, and then just touch base on hydrogen, because we know that hydrogen has already been one of the topics in previous IHEA webinars. So the first biofuel, which is a very popular one, is landfill gas. Landfill gas is a natural byproduct of the decomposition of organic materials in landfills. Landfill gas primarily consists of methane and carbon dioxide with small amounts of other gases and potential contaminants. The basic chemical composition of landfill gas is 45 to 60% methane, or CH4, 40 to 60% carbon dioxide, or CO2, other organic compounds that are non-methane. An example of that is siloxanes, and we'll talk about siloxanes a little bit further. And there's always traces of nitrogen and oxygen, coming from the air. And then also one of the contaminants that is a real hazard when we're talking about biofuels is hydrogen sulfide, or H2S. And then whenever we have biofuel that's generated in a landfill, there's always moisture involved. When we talk about the applications for landfill gas is often used in boilers and industrial applications by removing moisture and treating the fuel to remove the siloxanes, sulfur, and some of the other harmful contaminants. Siloxanes are organic compounds that are contain silicon and oxygen. When in contact together, form silica during the combustion process, which can deposit on equipment, surfaces, and affect the combustion efficiency, the emissions, and potentially damage the equipment. A landfill gas can also be used in reciprocating gas engines to generate electricity when cleaned of the contaminants that would otherwise harm the engine. So in your typical landfill, the gas is extracted out of the ground and then first goes through a moisture separator. From that moisture separator, the gas must be increased to a higher pressure in order to be used downstream. So there's often a compressor system in place then that sends the gas through another type of contaminant removal system, which will typically remove the H2S and often the siloxanes as well. Landfill gas, if not used elsewhere, is typically sent through a flare, which then exhausts the emissions from burning the landfill gas directly into the environment. But processed gas can be used for various applications, as we talked about, generating electricity, which is very common in landfills because the source of the electricity, being a gas engine, can be located very close to the landfill itself versus trying to have a pipeline for moving the gas to a different source. But landfill gas, once cleaned, can also be used for industrial processes, and then with some other processing, typically to remove the CO2, can even be put into the pipeline and used by residential people for residential applications. I know in my former career at Eclipse, one of the projects that we had for landfill gas was at a BMW plant in South Carolina. And there we used the landfill gas both to generate power for the plant and hot water in the facility, but also the burners in the paint shop or the drying ovens were furnished with equipment in the burners that could burn the landfill gas as well. When we talk about the benefits of landfill gas, capturing and using landfill gas as an energy source can help reduce greenhouse gas emissions and provide a sustainable energy resource. Landfills, as mentioned, are a major source of methane, which is a very potent greenhouse gas, much more potent than actually carbon dioxide. Capturing and utilizing landfill gas helps us to reduce the methane emissions, which is crucial for mitigating climate change. Burning landfill gas also reduces the equivalent CO2 that would have been produced by burning a fossil fuel like natural gas. To understand more about how burning landfill gas provides for carbon reduction, you can visit the EPA website, and under the Landfill Methane Outreach Program tab, they have a calculator where you can learn how to calculate the carbon reduction using landfill gas as a fuel. Other benefits from landfill gas are that the landfill gas can be converted to electricity, heat, or even pipeline fuel, as mentioned, if it's cleaned properly, thus providing for a renewable energy source that offsets the use of non-renewable resources like coal and natural gas. Another benefit of using landfill gas is it improves the air quality by reducing the odors, and other air pollutants, including those VOCs that were mentioned and the other hazardous pollutants that are taken out of the gas. And lastly, when we use landfill gas, we reduce methane and other pollutants from landfills, thus improving the local air quality, which reduce the health risks associated with emissions from landfills. All of these benefits combined can make landfill gas a valuable practice for both environmental sustainability and overall community well-being. So there are challenges when we use landfill gas. Landfill gas in its raw form has only about 50% the heat content of natural gas. Because of the lower heat content, landfill gas always requires us to modify the standard equipment in order to be able to burn the fuel. The nozzles themselves, because you're going to have to put in twice the volume of fuel to get out the same heat content, usually need to be adjusted, having larger orifices to maintain the same velocities. And because of the impurities in landfill gas, like sulfur compounds, the siloxanes, and the VOCs, landfill gas can damage the other equipment in the system and reduce the overall efficiency. Sulfur compounds in the exhaust gas from landfill gas can produce sulfuric acid when condensed. And as mentioned earlier, the siloxanes that are often found in landfill gas, if not removed, can form silica, which can plug the burner nozzles, damage your safety shutoff valves and regulators, and some of the other safety devices included in your fuel delivery system. Landfill gas typically requires quite a few enhancements to the burners, such as increasing the grade of stainless steel in the nozzles and the piping system, and acquiring special combustion system components in order to minimize the premature failure of the equipment. An example of that would be safety shutoff valves often have to be configured with stainless steel internals, or if they have standard rubber or NBR seats, those seats would need to be changed to a Viton or another material that can handle the corrosive nature of landfill gas. And in general, in our world, valve-proofing systems are always recommended when dealing with fuels like landfill gas, because they do a check on the leakage tightness of the valves each time you start your system, which is the safest way to ensure that you're not leaking fuel past the valves. And one of the last challenges with landfill gas is landfill gas can contain oxygen. And anytime you have oxygen in the presence of methane or fuel, it can result in a partially combustible mixture. And so most all landfill gas trains are furnished with flame arresters in order to prevent a backflash of the fuel back into the fuel lines themselves. The second biofuel that we'll talk about is digester gas, which is actually very similar to landfill gas in content. Digester gas is produced through a process of anaerobic digestion, which involves the breakdown of organic matter such as animal manure, wastewater biosolids, and food waste by bacteria in the absence of oxygen. Dairy farms are actually a great source for feedstock for anaerobic digesters that produce digester gas because of the large dairy herds produce a consistent flow of feedstock, which allow the dairy farms to generate their own electricity for their operation. So across the Midwest where I'm located, you'll quite often find dairy farms that have added their own anaerobic digesters, and then a power plant with reciprocating gas engines to produce their own local energy. Typical digester gas is anywhere from 50 to 75% methane, with the balance being carbon dioxide and 25 to 30%, with some of the same trace amounts of contaminants as landfill gas being hydrogen sulfide, potential for siloxanes, and then also water vapor. Typical applications for digester gas is that the digester gas, as it's removed, can be directly used as a fuel for burners in various industrial applications or in boilers. As with landfill gas, you must first process or clean the gas, removing the moisture and other sulfur compounds and siloxanes in order to use the fuel in burners or other combustion equipment. Further processing is also required in order to use digester gas in other applications like in pipelines. Digester gas can be used to generate electricity as a fuel for gas engines or turbines. As mentioned, if it's cleaned sufficiently, it can be used in the natural gas grid, injecting it directly into the same grid for applications that are used with your standard natural gas. And then when purified, it can also be compressed and used as CNG, which then can be used as a vehicle fuel. So as before with landfill gas, typical digester gas, goes through moisture removal first. If there's not a use downstream, it's typically flared. Then you have your siloxane and sulfur removal processing, and then compressing the fuel to be used as a biogas for heating, electricity, or other industrial applications. Or if it goes through the final CO2 removal process to purify the natural gas, it can then be recompressed and used in the natural gas pipeline as renewable natural gas. Some of the benefits of digester gas as a biofuel, like landfill gas, is it has a direct reduction of greenhouse gas emissions. By capturing the methane from the organic waste that would typically just be escaped into the atmosphere, the biogas systems prevent the gas from being released. Methane is significantly more effective at trapping heat than carbon dioxide. So capturing methane is extremely helpful in mitigating climate change. Since biogas is a renewable energy source that can be used to generate electricity and heat, and then used in other industrial processes or as a vehicle fuel, it reduces our reliance on fossil fuels and helps to lower the overall carbon emissions, which, as we know, the carbon footprint is the talk of the day these days. Anaerobic digestion also helps to manage organic waste by diverting it from landfills where it would otherwise decompose and directly release methane into the atmosphere. By using it, the waste product, it also reduces the volume of waste and makes the waste management process more efficient. One of the byproducts of anaerobic digestion, known as digestate, is very rich in nutrients and also can be used as a fertilizer. This also reduces the need for chemical fertilizers, which can also have a harmful environmental impact. Like landfill gas, anaerobic digestion of digester gas significantly reduces odors associated with the organic waste and improves the air quality around the waste management facilities and farms that have digesters. And then lastly, applying the digestate to agricultural land can improve the soil health by increasing the overall organic matter content, thus reducing the soil erosion, enhancing the water retention capability of the land itself. Like landfill gas, digester gas does have its challenges. In its raw form, digester gas has about 50% of the heat content of natural gas, which would require the same type of modifications to the standard fuel nozzles to burn the fuel efficiently. Also, like landfill gas, digester gas contains impurities like sulfur compounds, siloxanes, and the same kind of VOCs that can damage the equipment and reduce efficiency overall. Thus, burner nozzles and other piping systems need to be improved to the higher grade stainless steels. And your fuel delivery systems need to be upgraded with materials that can avoid the contamination and corrosion of the digester gas to prevent valve leakage and other premature failure of components. And as with landfill gas, we always recommend using a valve proving system to ensure that your safety shutoff valves have not deteriorated and are creating a leakage of fuel downstream. We mentioned that one of the byproducts of both the biogases, landfill gas and digester gas, can be renewable natural gas. So renewable natural gas, which is also known as biomethane, is purified biogas that has been conditioned to be suitable for injection into the natural gas pipeline. Typical renewable gas is 90 to 95% or greater methane, which provides for a quality that is almost exact or very similar to fossil fuel-based natural gas. The biogas, as we mentioned, used to create renewable natural gas typically comes from municipal solid waste landfills, digesters from wastewater treatment plants or livestock farms, food product digesters, or other organic waste management operations. And as mentioned, since renewable gas is cleaned and is pipeline quality, it can be used wherever standard pipeline natural gas is used today. So all of your industrial, commercial, and residential applications. The first liquid biofuel that we'll talk about is ethanol. Ethanol, also known as ethyl alcohol, is a colorless, volatile, and flammable liquid. It is commonly produced by the natural fermentation of sugars by yeast. Most of you may or may not know that ethanol in its raw form is a highly pure alcohol that can also be used for other purposes. And so when ethanol is produced for industrial process purposes, they add a small amount of gasoline so that the ethanol can't be mistaken for alcohol that could be used for human consumption. Ethanol has a chemical formula of C2H5OH, and as a biofuel can be blended with gasoline to produce gasohol, or as a liquid fuel can be used for various other applications. The most common use for ethanol is as a transportation fuel blended with gasoline to create the E10 up to E85 ethanol blends that we see at our gasoline pumps today. Whenever used as a fuel, ethanol helps to reduce greenhouse gas emissions. Ethanol can also be used to produce a sustainable aviation fuel that can reduce the carbon footprint of air travel. Ethanol can also be used as a fuel for industrial boilers. And in the ethanol production process, boilers are often used, and so the fuel can be recycled and used to actually fire the boilers that are used in the ethanol production process. And then ethanol can and has been used in other types of industrial applications using industrial burners that are suitable for liquid fuel, like a diesel fuel. One of the challenges using ethanol as a fuel for industrial processes is that it's often an economic discussion. The cost of making the fuel sometimes becomes cost prohibitive unless government incentives or other regulations dictate otherwise. The environmental benefits of burning ethanol is it produces less emissions as compared to fossil fuels, thus reducing air pollution and overall greenhouse gases. Since ethanol is produced from a renewable source, like corn, it has the benefits of all renewable fuels. And then because of the chemical composition of ethanol, it actually has a higher combustion efficiency than conventional fossil fuels. It has a higher octane rating, which leads to increased power and efficiency in engines. And then overall, it burns more completely than fossil fuels, leading to overall low emissions from the combustion process. Excuse me one second. Some of the challenges of using ethanol as a fuel are that ethanol is more corrosive than other types of fuels, which can lead to wear and tear on your burner system components and on the fuel delivery system. And in particular, it can be very difficult on the liquid pumps that are required to deliver the fuel at higher pressures to the burner. Ethanol also has a lower heat content than traditional fuel, thus requiring more volume of ethanol to produce the same amount of energy. And as compared to your standard diesel fuel components, they would possibly need to be increased in size in order to handle the increased volume required to generate the same BTUs per hour firing ethanol. Ethanol is also highly flammable and thus requires careful storage and handling. And ethanol also absorbs moisture when it sits for long periods of time. So the handling and storage of ethanol can produce a situation where moisture is absorbed and thus reduces the efficiency of the fuel, having the moisture involved. And of course, like any other fuel that's based from corn in particular, we always have the debate about food versus fuel when talking about using corn as the primary feedstock for ethanol production. The second liquid biofuel is biodiesel, which is a form of diesel fuel derived from biological sources like vegetable oils, animal fats, or recycled greases. Biodiesel consists of a long chain fatty acid esters and is typically made from fat. So the very basic chemical formula for biodiesel is represented as C17H34O2. When we talk about applications for biodiesel, we look at biodiesel as a B100, which means 100% biodiesel, or biodiesel can be blended with diesel fuel. An example of B20, which is 20% biodiesel. And then the different variations of B percentages can be used as a fuel firing boiler burners for residential, commercial, and industrial boiler applications. Biodiesel has become a very popular fuel in the Northeast United States, where oil had always been a popular fuel in the past due to the unavailability of natural gas pipelines. And in many cases in the older cities in the Northeast, you have very low gas pressure in the mains because of the old nature of the fuel systems themselves. And so even today, biodiesel is actually being used to replace natural gas burners in Northeast applications. Biodiesel can also be blended with diesel fuel for transportation use in diesel engines. And it can be used in any liquid fuel burners that are used today for industrial process applications. You know, some of the applications where you have, or I should say, we have seen industrial biodiesel burners is in metal processing, even food processing applications, chemical manufacturing, textiles. It's often used for agricultural drying, and then biodiesel can also be used in power generation applications using either a reciprocating engine or a combustion turbine to generate electricity. Very similar to ethanol, biodiesel produces fewer emissions than conventional diesel. It is made from renewable sources, thus it offsets the carbon emissions as compared to burning your conventional fossil fuels. One of the other benefits of biodiesel is it is biodegradable. So unlike diesel fuel, if it is spilled, it doesn't contaminate your environment because it's biodegradable. And then again, similar to ethanol, biodiesel has a higher cetane number, which improves the performance in engine applications and the overall combustion efficiency anytime it's burned. Very similar to ethanol again, there are challenges in using biodiesel as a fuel. Biodiesel can be more corrosive to certain materials used in burner applications. Biodiesel can produce higher NOx emissions. Since biodiesel contains oxygen molecules, those molecules can interact with the nitrogen in the combustion air stream, thus forming NOx at higher combustion temperatures. Biodiesel also burns much faster than conventional diesel fuel due to the higher octane number, which can cause localized higher temperatures and thus the potential for forming thermal NOx. Thermal NOx is NOx that is formed just due to the high temperatures that exist actually in the flame itself. Like ethanol, biodiesel does have a lower energy content per gallon as compared to regular diesel fuel. So your fuel system and burner components may need to be changed in order to accommodate the higher volume of fuel required. And biodiesel is more prone to oxidation, which can lead to the formation of sediments and acids in your equipment, which can cause premature failure and damage. The last biofuel, and it's a kind of a general category, is advanced biofuels. And advanced biofuels are commonly known as second or third generation biofuels. And that means the biofuels are going through a second or third process in order to actually create the fuel itself. Advanced biofuels are fuels that are manufactured from various types of non-food biomass sources, such as plant materials, animal waste, and other sources that are specifically captured for use as a source of fuel. Unlike first generation biofuels, which are made from sugar starch feedstocks, such as sugarcane or corn, or edible oil feedstocks like rapeseed oil and soybean oil, advanced biofuels are made from feedstocks that require special technology to extract them and use them, going through, as I mentioned, the secondary or third generation process. One of the examples that I've been involved with in my past as an advanced biofuel was distiller's grain waste. So in the ethanol process, there's a byproduct called distiller's grain that goes through a process to remove the impurities. And so the waste from the distiller's grain processing is called distiller's grain waste. And that particular waste then can be used as a fuel after it goes through a secondary process. And there are different ways that fuel can be used. If it's fermented, it can actually be used to produce bioethanol. It can be dried, and then after it's dried, it can be used as a direct material for combustion in solid fuel boilers or furnaces. The distiller's grain waste can also be used as a continuous feedstock for anaerobic digesters, or if dried and pelletized, it can be used as a solid fuel product for use in industrial burners, typically on in industrial boiler applications. Similar to the other biofuels, typically economics becomes the biggest factor in any decision to create an advanced biofuel. And usually you'll find that the only time these fuels go through that second or third process to generate the fuel, there's some type of government incentive or regulation in place that provides the incentives in order to justify the creation of that biofuel. The second type of fuels that we talked about as a renewable fuel are synthetic fuels. And synthetic fuels can be either liquid or gaseous fuels that are produced from various feedstocks through a chemical conversion. Syngas, as an example, can be derived from the gasification of coal, biomass, or other solid feedstocks, or by reforming natural gas. Liquid synthetic fuels can be refined using the Fischer-Tropsch conversion process, which converts a methanol to gas conversion, or by direct coal liquefaction. The Fischer-Tropsch conversion is a chemical reaction converting mixtures of carbon monoxide and hydrogen in the form of a syngas, which is usually a byproduct from a process, into a liquid hydrocarbon, typically in the presence of a catalyst under very high pressures. And then e-fuels are synthetic fuels that are manufactured using carbon dioxide or carbon monoxide when combined with hydrogen to create a sustainable electric power for renewable sources. So e-natural gas is an example of a e-fuel created synthetic fuel. So syngas is created through biomass gasification, which is a common method for producing the syngas by converting organic materials into hydrogen and a carbon dioxide mixture. So the process of producing syngas using biomass is that you first must dry the biomass feedstock to reduce the moisture content, making it much more suitable for gasification. Then that feedstock that's been dried goes through a pyrolysis process where it's heated without oxygen present, which causes it to decompose into a volatile gas in a solid char, almost like a charcoal. Then the volatile gas and char composition is burned with a controlled amount of oxygen to produce heat, and a carbon dioxide and water mixture. Finally, that heat generated in the combustion process drives endothermic reactions in the reduction zone, which is a zone without oxygen involved, which converts the composition of the fuel to carbon dioxide, converting carbon dioxide and water into carbon monoxide and hydrogen, which are both fuels, which is what we call syngas. The syngas has a typical lower heating value of around 120 BTUs per cubic foot, which for those of you who know is a very low BTU content, as your typical methane or natural gas heat content is about 1,000 BTUs per cubic foot. So the typical composition of your syngas after it's created is 30 to 60% carbon monoxide, 25 to 30% hydrogen, 5 to 15% carbon dioxide, a little bit of methane, and then you always have some water vapor and some other trace compounds like sulfur. And then typical contaminants might be some traces of ammonia, or other things like your siloxanes. In order to use syngas as a fuel, it does require very special attention to the burners and other components in order to deliver the fuel safely to the combustion system and actually burn the fuel. One of the keynotes to mention with syngas is the hydrogen content. You know, when we talk about our sustainable future, hydrogen is often mentioned as an important part of the sustainability using gaseous fuels for industrial processes. And syngas or synthetic fuels have been around for years. And so there's a lot of knowledge that exists in the industry for burning fuels that have a high percentage amount of hydrogen. We talked a little bit about the fact that e-natural gas is also a synthetic fuel. E-natural gas is produced when we combine green hydrogen and carbon neutral carbon dioxide. Carbon neutral carbon dioxide is carbon dioxide that is captured from industrial emissions directly captured out of the air or from biogenic sources. E-natural gas is created through what is called the Sabatier reaction, where the green hydrogen reacts with CO2 in the presence of a nickel catalyst at high temperatures and pressures, thus producing methane and an exhaust with water. E-natural gas is chemically identical to fossil fuel natural gas, and thus can be used and added to the natural gas pipelines, making it suitable for all types of industrial applications where conventional natural gas is used today. E-natural gas also has several environmental benefits. Like other biofuels, it reduces greenhouse gas emissions by using captured CO2 and renewable hydrogen. It burns cleaner than conventional fossil fuels because it typically has a higher methane content. Because it's produced from renewable sources, it can be carbon neutral when you use green hydrogen and captured CO2 in the production process. E-natural gas can be transported and stored using the traditional natural gas infrastructure. And using e-natural gas can reduce our reliance on imported or other typical fossil fuels. Like other special fuels, e-natural gas does come with its challenges. Today, it is a very costly fuel. It costs a lot of money to produce natural gas, so it's cost prohibitive as compared to the natural gas that we're used to today. The total energy efficiency of e-natural gas is lower than other renewable energy sources because of the energy required to produce the fuel. And while e-natural gas is considered pipeline compatible, there can be traces of components in e-natural gas that do require it to be handled a little bit more special with modifications or upgrades to some of the fuel delivery systems that would come in contact with e-natural gas. And the last challenge with e-natural gas is the sustainable carbon dioxide sources required to manufacture e-natural gas currently can be unreliable and can be a limited factor in e-natural gas production. The last field that we'll just touch base on, because it's been discussed in other IHEA webinars, is renewable hydrogen. And renewable hydrogen or green hydrogen is hydrogen produced from renewable sources such as wind, solar, or hydropower. Renewable hydrogen is produced through an electrolysis process using that renewable energy source. Or thermochemical processes using heat from renewable sources and chemical reactions that release the hydrogen from organic material. Renewable hydrogen can also be produced from photolytic processes where water is split into hydrogen and oxygen using sunlight. Biological processes where algae or other bacteria can be used to produce hydrogen, or through a pyrolysis process, which we talked about previously, where you heat the organic material without oxygen present to form hydrogen and carbon monoxide. So what will determine the future of renewable fuels? Technological advancements, such as innovations in renewable energy technologies, including more efficient solar panels, wind turbines, and biofuel production methods, will play an important role in the future of renewable fuels. Advances in energy storage solutions like batteries and hydrogen storage are also essential to manage the intermittent nature of renewable energy sources moving forward. Policy and regulation. Government policies and other international agreements, as noted, will significantly influence the adoption of renewable fuels. The incentives for renewable fuel projects, carbon pricing, and other regulations limiting greenhouse gas emissions can directly drive the transition to cleaner energy resources. The most important factor for the future of renewable fuels is the economic situation. The cost of renewable energy technologies compared to fossil fuels has a definite impact on their adoption today. As the cost of renewable energy sources continues to decrease, it becomes more competitive with traditional energy sources. Market demand. The private demand for sustainable fuels in various sectors, including transportation, industry, and residential use, will also have an effect on the growth of renewable fuels in the future. And of course, the environmental and social considerations are always going to play an important role in our decision to adopt renewable fuels, even at higher expense. And the last challenge for the future of renewable fuels is the feedstock availability. The availability of the raw materials that we use to produce biofuels and other renewable fuels will definitely have an impact on the future scalability of the renewable fuel. So developing new feedstocks and improving the efficiency of existing ones will have an important part in the growing demand for renewable fuels in the future. So to summarize, renewable fuels offer a sustainable alternative to conventional fuels by playing a crucial role in the future reduction of greenhouse gas emissions, the enhancement of our energy security, and the promotion of a sustainable environment. As technology improves in the future, the cost of generating renewable fuels should become more attractive, allowing for them to become a more important part of our overall fuel portfolio. And as Jason mentioned at the beginning of the presentation, IHEA is putting together an industrial heating decarbonization summit at the end of October. We'd be more than happy to have you join us to learn more about how we can work together to forge a sustainable path for the industrial heating industry and reduce the carbon footprint of industrial heating processes. So the end of October in Indianapolis, we'd be more than happy to have you join us. At this time, I would open up for any questions.
All right, thank you, John. No primary questions in the chat box, but can we review or take a look at how you calculate your carbon reduction again, achieving, like if you're using a landfill gas? And I guess the extension part of that question from me would be, is there anything else for the other fuels to help you calculate your carbon reduction?
Well, the different associations that are involved with the different fuel types typically have a calculator to help calculate the actual emission reduction when you burn some of these renewable fuels. In particular, I mentioned at the beginning that for landfill gas, the EPA has, as part of their landfill methane outreach program, or LMOP, a calculator on their website that is just basically an Excel spreadsheet that goes through and self-explanatory, allows you to put in some of the basic information on what you would be doing to burn that fuel, and it gives you what the carbon reduction footprint would look like.
Okay, thank you. Hearing really nothing else at this time, I'd like to say thank you to everybody for, again, attending our webinar. Like I mentioned in the beginning, and John just mentioned at the end, we've got our Industrial Heating Decarbonization Summit coming up again in October, so hope you can join us for that. And finally, again, watch your email for a link to a survey, and please take a few minutes to share your feedback with us. On that note, we'll wrap this up, and everybody have a great day. Thank you.
Thank you, everyone.